right, so for the past 4 lectures, we've built the whole machine, right? The physics, the equipment, the nuts and bolts of image quality. But now we have to face the other side of that equation, the cost of every single image we take, and that cost is measured in milligray. Let's really dig into what that means. This quote from Dr. Mohammed Jafar just hits the nail on the head, doesn't it? This whole explainer isn't just about numbers and physics, it's about an ethical balancing act. The entire practice of mammography hinges on managing this tiny risk from radiation to achieve the absolutely massive benefit of catching cancer early.
So why all the fuss about dose in mammography? I mean, what makes it so different from, say, a chest x-ray? Why is this conversation so incredibly critical here? Well, it all comes down to a perfect storm of factors that we just don't see anywhere else. Just think about how these things stack up. First, unlike most imaging, we are screening a huge population of women who are, for the most part, completely healthy. Second, we're targeting an organ, the glandular breast tissue, that we now know is one of the most radiosensitive parts of the body. Third, those special low-energy x-rays we need for good contrast, they get absorbed very efficiently. And all of that leads us to the central, kind of mind-bending paradox of mammography. We have to use a known carcinogen, radiation, to find a cancer that can itself be induced by radiation. That is a heavy responsibility.
So if we're going to manage this cost, we have to be able to measure it. And not just measure it, but measure it accurately. We can't just slap a detector on the skin and call it a day. We need to know the dose to the specific tissue that is actually at risk. And that, my friends, is where the concept of mean glandular dose, or MGD, comes into play. You might think, well, let's just measure the dose right where the beam enters the skin. That's called entrance surface dose, or ESD. But here's the thing, the skin isn't the primary concern. The real risk is to the glandular tissue deep inside the breast. And that's exactly why the industry standard, the gold standard, is mean glandular dose, MGD. It's a calculated value that gives us the average dose specifically to that critical tissue. It's the number that truly reflects the biological risk. So how do we actually calculate MGD? Well, the international standard is a really elegant formula called the dance method. It all starts with a simple measurement called incident air kerma, which is basically the raw radiation dose measured in the air right before it hits the breast. Then the formula applies a series of super smart correction factors to figure out what that raw dose really means for the sensitive tissue inside. Let's break it down real quick. The G factor is all about the beam's energy and how thick the breast is. The C factor corrects for the breast composition. Is it mostly dense glandular tissue or more fatty? And finally, the S factor accounts for the specific X-ray recipe, the target and filter combination used. Each little piece of the puzzle refines the calculation until we have a really accurate estimate of the dose that matters. Now, to make sure we're all playing by the same rules, so a machine in London can be compared to one in New York, we need a universal benchmark. And that's where the standard breast comes in. It's not a real breast, of course. It's a phantom made of 45 millimeters of a plastic called PMMA, and it acts as the perfect stand-in for an average breast. All our reference levels and safety checks are based on this guy. Okay, so we can measure the dose with incredible precision. But the real question is, how do we control it? In the real world, what are the levers that technologists can actually pull to make sure that dose is as low as reasonably achievable for every single patient who walks in the door? You know, a whole bunch of technical things come into play. The energy of the X-ray beam, the use of an anti-scatter grid, which can double or triple the dose, by the way, the efficiency of the digital detector. They all have an impact. But as you can probably guess from the highlight here, there is one factor that stands head and shoulders above all the rest. Yeah, just look at that number, 30 to 60%. That is the absolutely staggering dose reduction we can get from one single action, good breast compression. It's incredible. Just to put it in perspective, for every centimeter of thickness we can reduce through compression, the dose can drop by half. It is without a doubt our most powerful tool. So yeah, let's just say it loud and clear. Compression is king. And it's not even just about the dose. Good compression makes the breast a uniform thickness. It spreads all the tissue out so things don't overlap, and it holds the breast perfectly still to prevent motion blur. It makes the picture better, and it slashes the radiation cost. It's a total win-win. Okay, so we've been talking a lot about the cost, about the risk, but that's only one side of the coin. That risk is only acceptable because the benefit is so monumentally huge. So let's actually look at the numbers. What does this benefit versus risk equation really look like? Let's start with the risk side. The best data we have suggests that for every 100,000 women who are screened regularly throughout their lives, the radiation exposure might, and that's a big might, be responsible for inducing about 2 fatal breast cancers. That's the risk. And now, here is the benefit. In that very same group of 100,000 women, that very same screening program will find somewhere between 300 and 500 cancers at an early, treatable, and often completely curable stage. I mean, just look at that comparison. Visually, it's not even a contest, is it? 2 versus 400. This gives us a benefit-to-risk ratio of somewhere between 150 to 1 and 250 to 1. The benefit just completely and utterly overwhelms the risk, and this is the fundamental justification for screening millions of healthy women.
Let me give you one more exam-ready number to put that risk in perspective. For a woman in the typical screening age range, the risk of a fatal cancer from one single standard 2 milligram mammogram is about 1 in 50,000. Now, it's important to remember that at these low doses, we're only worried about stochastic or chance-based effects. And this risk isn't the same for everyone. It actually goes down the older a woman is when she's screened, which is a big reason why screening programs usually start around age 40 or 50.
This incredible benefit-to-risk ratio, it's not an accident. It doesn't just happen by luck. It's maintained and protected by a robust safety net of regulations, scientific bodies, and quality assurance programs that are always evolving to keep patients safe.
And that science is constantly being updated. A perfect example is the tissue weighting factor. It's just a number that tells us how sensitive an organ is to radiation. Back in 2007, based on new evidence, the International Commission on Radiological Protection more than doubled the weighting factor for breast tissue, bumping it from 0.05 all the way up to 0.12. That change was a huge deal, and it really reinforced just how important all of our dose-saving efforts truly are. A key tool in that safety net is something called the Diagnostic Reference Level, or DRL. Now listen, it is crucial to understand this. A DRL is not a legal dose limit. It's not one line you can never cross. Think of it as an alarm bell. It's an investigation level. If a clinic finds that its average dose for a standard breast is consistently creeping above that DRL, it automatically triggers a review to figure out why and fix it. It's a brilliant tool for continuous quality improvement. Finally, let's just put the dose from a mammogram in context with other things. To do that, we have to convert our MGD into what's called an effective dose, which helps us compare different types of exams. For a standard mammogram, that's about 0.4 to 0.7 millisieverts. And as you can see, that's roughly the same as a plain abdominal X-ray. It's only a fraction of the natural background radiation we all get just from living on the planet for a year. And it's absolutely dwarfed by the dose from a CT scan. So where does that leave us? The moral equation today is clear, and the benefit is overwhelmingly positive. But the guiding principle, the North Star of radiation protection, is ALARA, as low as reasonably achievable. The question we have to keep asking ourselves is, as our technology gets better, as our detectors get more sensitive and our software gets smarter, how will our definition of reasonable continue to change? How can we make this life-saving exam even safer tomorrow?